All right, Year 10, so what we're looking at today is specifically how we can go about approaching this new type of assessment task. So the goal for this physics unit is to essentially prepare you as best as possible for the upcoming senior and the changes that have occurred to senior. So some of the things that have changed is the style of report and the style of assessment. So we're trying to prepare you for, in this term, we're trying to prepare you for the student experiment, which is a new type of assessment which pretty much replaces the old EEI, or the experimental investigation. Very similar to what we've been doing in the past, so just a few things you need to be aware of. So you've been practicing for this without realising it for the last 3 to 4 years at Mercy, but we're going to make some changes to how things are done and stepping up a few of the things that we're doing this year, and specifically looking at trying to get you as well prepared as possible for the new assessment when you sit in Year 12. Okay, so this will make up 20% of your final grade, your approach to this in physics, and if you're doing it in chemistry and biology, well then this will make up a fair portion of your final grade when you walk out of Year 12. So it's really important that you nail it, and it's really important that you try and make your mistakes now and get your head around the idea of what's going on. So if you don't give it a red hot crack in Year 10 and Year 11, you're going to find it really, really difficult to get a quality student investigation or student experiment when you walk out in Year 12. So I'll talk about each segment and we'll try and break apart what's going on, what the changes are and how that affects what you'll be doing. Okay, so no longer do we have an aim. Okay, no longer is it, in the old school, in the old report we'd have to investigate blah, blah, blah. That's no longer the case. What we've got is a research question. Very, very similar. Okay, and in this task you'll be given your research question, but it might be to identify the relationship between. So in this investigation, something along the lines of to investigate the relationship between mass and acceleration in a mousetrap racer, given the mousetrap racer is propelled on a horizontal plane with equal elastic potential energy. Something along those lines. So no longer do we have a name, we now have a research question. Again, this one you'll be given it, but as we progress our way through, you'll have to make your own research question up. The rationale, now this replaces the introduction in the old report system. It's something you're probably not that familiar with, but the introduction is essentially where we find our 3 or 4 key physics or science concepts, and that's how we bring them up, so that when imagine someone's reading your report, this is the stuff they'll need to understand to get your report. Now this shouldn't just be descriptors about what's going on, there should be more than just descriptions. You're going to need to have some equations and some expected relationships. So realistically, this should be informing what you think is going to happen. Okay, so I'll try and give you an example that helps out here. So if I was doing a rationale on the acceleration due to gravity, okay, the first thing I would put in is what is gravity, how does it work, why does it work. I'd have, gravity is a force of attraction between any mass, it's proportionate to the size of the mass and inverse proportionate to the distance. I'd then have my equation, okay, so I'd have to be referencing my equation F equals K m1 m2 divided by d squared. Okay, that's the force of gravity, the equation for the force of gravity, and depending on what variable I was changing, that would tell me the type of change I was expecting. So if I was increasing the mass, I would expect that as mass goes up, force goes up linearly. If I was adjusting the distance, if I was increasing the distance, then I'd expect as distance goes up, my force goes down at a rate of 1 over distance squared. Okay, so that's what I'd be expecting. I'll talk a little bit more about the rationale specifically later on, but that replaces our introduction, and it needs to be pretty physics heavy. You should be using sources, so sources from information from external sources, reliable sources, not www.physicsiscool or whatever. You need to make sure you're getting it from reliable sources and referencing that later in your report. This is one of the big changes. Okay, one of the big changes is no longer do we list our materials, list our method, and go from there. You'll be given an experiment. So in this situation, we're given the balloon experiment where we bob the balloon and release the balloon and see how far it goes with a changing mass. And you have to make a modification. So you've got to make your own experiment as a modification to a pre-existing experiment. You need to justify why your experiment is better. Does that make sense? Don't know why I'm asking, there is no one in the room. But what you're trying to do is to create an experiment that is an improvement on the experiment you've already done, and justify what. So in this example, for example, one of the problems with the experiment that I've created is that when you blow the balloon up, you have no way of assessing the size of the force the balloon is putting out. So you have no way of assessing the driving force on the car. That's one of the problems. Now you might need to adjust your task so you can better address the research question. Cool? Similar with, we'll go to the next section. Results, analysis, and calculations. I've grouped these into 3 sections, okay? Because results, we do up a big table. Analysis, we find gradients, we find relationships, and we talk about averages and all sorts of things. And calculations is where if we've manipulated results at all, which you might need to do in this experiment, I won't tell you, but you might need to do some calculations to find out what you want for the research question. Anything in that regard is much the same. You probably haven't had a whole lot of exposure with that. We'll get our head around that idea, but it's very similar as it was in the old reporting system. However, there's a greater emphasis on uncertainty, and something that you haven't been familiar or exposed to at all is this idea of mathematical uncertainty. Being able to say this is how certain over my results, putting a percentage on it. We'll come to that later. Okay. In physics, analysis must involve a mathematical model. Okay. Mathematical models are things where we are predicting what will occur or what has occurred using some y equals x, or y equals something x, y equals something over x. Some relationship which we can describe mathematically, which allows us to predict what's going to occur in the future and what will have happened prior, what will happen between results. So we can extrapolate data depending on our model if we've got a very good model. So we need to talk about accuracy and all sorts of stuff. Again, we'll talk about that later. There's a lot to take in. The discussion is no longer called the discussion as such. It's just 3 subheadings that must be addressed, but it's the old school of discussion, okay? Where we used to, what are the results say, how do they link to the hypothesis, how does this link to theory, what are some errors, what are some modifications. That's now gone. We've now got 3 different subheadings, and they're pretty much equally sized. So you need to be really aware that there's probably a greater emphasis on evaluation, which is errors, the old school errors, evaluation of the experiments or process, and suggestions for modifications or improvements and extensions. Now, I'll come back to that in a second, but bigger emphasis on those 2 in brief. So the interpretation of evidence, that's saying, did your data match the rationale? Did your data match what was expected in the theory? So you look at your analysis, you look at your uncertainty, and you say, how certain are you that your data matches the rationale? If it does, great. What's your wiggle room? If it doesn't, that's fine. Why not? Why didn't it match? What went on with your experiment that allowed it not to match the rationale perfectly? Okay, you'd be talking about the fact that your trend line or whatever falls or doesn't fall within your mathematical model, your uncertainty and your error bars. You'd be talking about all that sort of stuff. That's where you talk about your results and how they link to the theory. The evaluation of your experimental process, that's you taking a critical look and saying, well, what happened in our experiment or in my experiment? Obviously, we're still not using first person, we're using third person past tense. But what happened in the experiment? Could I see any places where there was error? So were there anomalies that occurred? So if I'm looking at my results and I'm identifying anomalies, were there any anomalies occurred? Why did they occur? Were those anomalies there for a reason, or was it just poor testing, or how can I go about sorting that out? Saying things like we mucked around, we didn't use our time efficiently, we didn't measure properly, that's no good. We don't want to see that sort of stuff in our evaluation of experimental process. We want to see the evaluation of the method that you've written down, not the one that you've run. If there was a problem with your method because you mucked around, retest, okay? Retest, redo it, do it properly, do it exactly how you've said that you do it in the modification, in the method, and then your evaluation of your experiment should be something about precision, should be about things like friction should definitely come up in this experiment. As you change in the mass, that might change the frictional force or might change the driving force. There's all sorts of things you can talk about in their distribution of mass, plenty of stuff that you can mention in the evaluation of the experimental process here. And then suggestions for improvements and extensions. So your improvements obviously should link to anything that you've identified as an issue in your evaluation. Extensions is I like it. It's a really good way of showing that you understand the topic, because you can then say, this is what we tested this time, but potentially next time we could look at this, and this would give us a greater idea about what's going on, okay? Maybe we could adjust the friction, maybe we could do all sorts of things to get a greater idea about what's going on in this concept, okay? So it is a little bit different in a lot of ways, okay, and definitely the quality of the writing and the fact that you'll need to be referencing, and you can't get away with not having a literacy upper standard. You need to be a pretty good writer, but in saying that, if you stick to these subheadings and think about them in the way that you've thought about the old report, but making a few adjustments, you can find success in this task. You really need to ensure that you're giving it a really good crack, okay, otherwise you might find that when you get to the senior, it's too much of a jump. So you need to be trying to make the steps early. Using the scaffolding, we've given you the research question, we've given you an experiment to run with. You're pretty familiar with the theory behind what's going on. This is all about Newton's laws and all sorts of stuff that you've dealt with before, maybe energy transfers depending on which way you go. Okay, so make sure that you have a really good crack at this. If you've got any questions, please let me know. Apart from that, let's go banana.